So, I thought I would try before the break to review generalized complex sinusoids in S-plane and Z-plane, just to finish that off. And then after the break, we'll do geometric signal points of view. So, generalized complex sinusoids. So, let S be a complex number, and we'll break it down. Its real part is sigma, and its imaginary part is omega. And so this is some number in the complex plane. So I can say this is any point in the complex plane. All right, so you can plot it. And because we're using S for our variable, we'll call this the S-plane. But it's just a complex plane. It's only called the S-plane because we call the points in it S. And for the Z-plane, it's also just the complex plane, but we'll call those points Z. And it'll help us keep track whether we're talking about continuous time system or discrete time systems. But it's still just the complex plane. All right, so let's let this be a particular S. So that's S equals sigma plus j omega. And maybe I'll give it a subscript so there's no confusion about the general sigma. So this would be sigma 0 here, and then here is omega 0. So those are just the coordinates of S0. All right? We'll put this in a circle to keep it separated. All right, so now, let's define a signal x of t as, okay, let's say GCS would be our abbreviation for generalized complex sinusoid, so that's what I'm defining here. So our generalized complex sinusoid, x of t, is defined as e to the st for any s. And so that breaks down into e to the sigma plus j omega t. And by properties of exponents, we can factor that into an e to the sigma t times e to the j omega t. So this, e to the sigma t, let's also define sigma equals, by definition, minus 1 over tau. Then we can also write it as e to the minus t over tau, which you might remember is the canonical definition of an exponential, times e to the j omega t, which we know how to break down by Euler's identity. So what we can say then is that this is a unit amplitude exponential, which is the new part, that's the generalization part, times our old friend, the complex sinusoid. So a generalized complex sinusoid just adds an exponential growth or decay to the complex sinusoid. It's just an amplitude envelope. But we only have unity amplitude, and the complex sinusoid is also zero phase. We don't have a phase control. So to add those back in, we just need to multiply by another complex number. So let's say we're going to add amplitude and phase by forming x of t as complex amplitude times e to the st. And that's the same as, if you recall our definition, kappa of Roman a e to the j phi times e to the st. And so you all know how to break this down. This will now give us an amplitude times an exponential at time constant tau times cosine omega t plus phi plus j sine omega t plus phi. So that's what you can do with a point in the complex plane. Actually, 2 points. So one point, so what are the parameters? The parameters of the generalized complex sinusoid are the frequency omega, the time constant of decay tau, and then we have and these are in S. S equals sigma plus j omega, which is equal to minus 1 over tau plus j omega. So sigma we can think of as the rate. It's the exponential decay rate, and 1 over that is the time constant. Well, minus 1 over that is the decay time. So those are two parameters. Then we also have the amplitude and phase, and those are in the complex amplitude a e to the j phi. And just to go ahead and write it up here. So this is the compact representation. It's an exponentially decaying or exponentially growing complex sinusoid parameterized by S in the S-plane, which has a decay rate and a frequency built into it, and another point, which is the complex amplitude in the usual way. Now you might be tempted to say that S is complex frequency, but I would caution you against that, because complex frequency comes up when you let omega go complex, and it might be kind of confusing. But you can call S the natural frequency. You see that in textbooks. Because when we get into systems analysis, we'll find that that linear time invariant systems all ring with exponentially decaying sine waves. That's the only thing that comes out of them. And so those are called the natural frequencies of the system. So if you go up to a pile of springs and masses and hit them, those are the things that come out. You get exponentially decaying sine waves coming out. That's all they can do. All right, so that's essentially what we need from the S-plane. We need each point to give us one of these exponentially growing or decaying sine waves. Now, we saw this picture. Let's look at the picture again. This is all the cases that you get. So this is the real axis of the S-plane, which is the sigma axis, or minus 1 over tau axis. This is the imaginary axis, which is the j omega axis. So frequencies go up along this axis in the S-plane, and they go more and more negative when away from 0 to the downward direction. And so to the right, sigma to the right is positive growth, and sigma to the left is negative exponential decay. You know, it's the negative sigma is positive tau. So a time constant that's positive gives you a decay that's tau seconds long. Tau is the 1 over e time, remember. And remember that T60 is about 7 times tau. So it takes about 7 time constants to decay 60 dB. On the right, you don't get, the T60 is infinity. A true time constant would be infinity. Or you could say a negative tau is a time constant to the left. So if you go backwards in time, that's your decay time. Your 1 over e decay time backwards in time is tau when it's negative. So these are the various cases. So here's some various exponentially decaying sine waves. All right, so that's the S-plane. And notice the title here. This is the domain of Laplace transforms. What is the domain of the Fourier transform? You know, I've written down the Fourier transform, and if you, actually I'd rather say the range. If you think of functions having a domain and a range, what is the range of the Fourier transform? What is the output of the Fourier transform? It doesn't hit anywhere in this plane. It only hits along certain points. Do you know where those are? Yep, it's the j omega axis. So the Fourier transform takes a time signal and gives you a complex function that you can plot along the j omega axis in the S-plane. And so that's why we call the j omega axis the frequency axis of the S-plane. So and it turns out that the Laplace transform, if you only specialize it to the j omega axis, gives you the Fourier transform. So the Laplace transform is a generalization of the Fourier transform, just the way we generalize complex sinusoids. So instead of taking an inner product of your signal with a sinusoid, you take an inner product of your signal with an exponentially decaying or growing sinusoid, and that gives you all these other points. So you can think of the Laplace transform as just continuing the Fourier transform out into the complex plane. And so that's very, very useful for systems analysis, which we'll see later. So that gives us the question, why S? And it comes from the definition of the Laplace transform.